Hello statistics student, this video is for chapters 3.1 and 3.2 part 3. We're going to talk about more about the three basic probability description: probability of A and B, probability of A or B, probability of conditional probability, and maybe complement also. So for example, before that we want to talk about a particular kind of contingency table which describe drug tests or clinical diagnostic tests. So if we have some job applicant or whoever that needs to do a drug test drugs, so we can have a table that summarize the results. Sometimes you would catch someone that actually took drugs because the drug test shows positive, so that is a correct diagnostic or correct results. But sometimes because of biological differences between people and how they react to drug testing material, so you can have someone that tests positive but it actually does not use drugs. So we call this false positive. And likewise, we could have a false negative. Negative means the test results show that you did not use drugs, and you actually did not. Then this is a correct diagnostic, but you could show that you did not use drug, but actually you are a drug user. So this is called a false negative. So false positive is when a subject does not use drugs but get a positive result claiming that this person used. False negative would be someone that did not use drugs, but the test does not detect it. So why would people know that? Maybe it is the person that actually knows he or she take drugs and then do the test, so we would know how accurate a particular test is. Just like the COVID-19 tests, there's two types of tests. The faster one has a very high false positive, or is it false negative rate, but the slower and expensive one is more accurate, and the false positive or false negative is really low. It's quite accurate, but it takes a longer time. So the same can be true for people doing not a drug test but a clinical disease test. So maybe you do a TB test or you do an X-ray to check if you have a certain disease, and then a positive means that you have that disease, and then so if you have the disease and you get positive, it's correct, but if not, then it's a false positive. If the test results show negative, you undergo more testing and it shows that you actually have the disease, then it's a false negative. Otherwise, it's a correct, right? So let's do an example on this. And later on, when we do statistical analysis, sometimes we run into a situation. Our statistical analysis shows that a particular value is equal to a number, but actually could be wrong. So we could have this kind of situation. So we like to know how to understand them. So this is a contingency table of a drug test. For what is the grand total? The grand total would be 10, 8, 4, 400. All add together is 422. So we want to find the probability of a positive result. Take one person. So this is always one person or one subject. So what is the probability that that subject had a positive result? So you look at all the positive with 14 divided by the grand total is 0.033. So actually not too many people take drugs, so it is a very low chance of having a positive result. It's lower than 0.05. You say it is unlikely to get positive. So would it work if the subject actually uses drugs? So given that a subject uses drugs, you yourself know that you use drugs, what is the chance that that person get positive? So sometimes a person will say, well, positive rate is really low, so I should just go take it because I won't be caught. So, but it turns out that because of conditional probability, it is not the same. So if you use drugs, so you would be looking at only this row, right? The total people that use drugs is 18, but they catch 10. Positive means they catch you, right? 10 out of 18 is 0.556, so there's 56%. It's not very high, but it's a higher chance than 3%, right? Or high chance than 0.033. So that is 0.556. So if a subject uses drugs, there is a higher chance of getting the positive test results. So that's the difference between having a particular category when you do not know the two other category versus one. So this particular comparison, comparing probability positive and probability positive given that he has used drugs, will lead us to analyze a situation called independence. We'll talk about those. So in 3.1 and 3.2, the books also talk about some other terms called mutually exclusive. This is a statistical term. If they say mutually exclusive, they're talking about two events. They're mutually exclusive if they will not occur at the same time. Of course, we are still talking about selecting one, okay? We're not talking about selecting two events or selecting two person. Picking two person will be in 3.3 and 3.4. So we are only talking about one person, but it has two kind of category. So your probability of A and B is equal to 0, like in this two-way table. They will all ask a particular question. Male had 1 answer yes, 4 answer no, 2 no opinion. But for female, they have 5 answer yes, 2 answer no, but 0 no opinion. And obviously, you can 0 means female and no opinion will not happen together. So we'll say female and opinion are mutually exclusive. Two things and together. So if you see a two-way table that has a 0 number, that means the row column and the row column and the row and the column variables are mutually exclusive. And if the two are mutually exclusive, then when I do probability of A or B, I just add them individually because I don't need to subtract probability of A and B. So that is mutually exclusive. The second term that we want to understand when we look at events is independent events. So we have two events. Okay, we want to classify if they are independent. Okay, so still remember this is one selection or one event. We're not talking about doing two events that doing one and then like you toss 2 times. We're not talking about tossing 2 times. So tossing 2 times also have independent, but it would be in the next section in 3.3.3.4. So in 3.1.3.2, we are talking about always doing one procedures, looking at one selection and looking at one sample subjects. So how do I know if two events are independent? Like I pick someone that's female and no opinion. How do I know? Oh no, that's mutually exclusive. So how do I know that female and no opinion are independent? They don't affect each other. So you can check one of the 3. Okay. So we say two things are independent, A and B are independent if A and B is equal to A times B, probability of A and times probability of B. Or because A is independent of B, so the probability of having A is the same as probability of having A if B has already occurred. So whether B occur or not does not change the probability of A. Or probability of B occur is not depending on whether A has occurred or not. So use conditional probability to check if they are independent. So this would tell if A and B affect each other. If A and B affect each other. So let's look at one example would be, you want to pick a student and you want to see if a female student choosing like engineering major, are they independent? Like with female student choosing a major is dependent on the gender, right? So these are the things that we want to do. So it basically lets you analyze if two variables, two categorical variables affect each other. So if I know the gender, would it affect the major? If I know the gender, would it affect their choice of phones? So we can use a two-way table to do that. And this is actually the most important things in chapter 3.1 and 3.2. Being able to use a two-way table and check if two random variables affect each other. So we want to ask, if iPhone use independent on gender, does gender affect the use of iPhone. So the way to check is we say we can check either one of them, right? Either multiplying or check using the conditional probability, see if it is the same as not using it. So we would use the conditional probability first. See if probability of using an iPhone is the same as someone is a female using iPhone. Does being a female change the probability of that person using an iPhone? If it does, that means it is dependent. If it's the same, then it is independent. That means your gender does not affect the probability of someone using iPhone. So first of all, probability of iPhone is how many people use iPhone? It's 18 plus 24. The grand total adding 1, 2, 2, 4, 18, 24 is 52. So it's 0.824. But probability of iPhone over or given it's a female would be you only look at the female row. So you add the total female, 24 plus 4 plus 2 is 30, right? So it's total female is 30. So basically, you just do out of all the 30, how many use iPhone is 24. So it's 0.8. So these two are not the same. So it seems like if it is a female, the probability of a female using iPhone is lower than any person using iPhone. Any person using iPhone is 0.82. 82%. They are very close, but they are not the same. So strictly speaking, if probability of iPhone and probability of iPhone given another gender are not exactly equal. So when we do chapter 4, we're looking at exactly equal. So then we say they are not independent. The gender does affect them. They affect the choice of phone. We conclude that iPhone use is dependent on gender. So if it's male, the percentage is different, the chance is different. If it's female, the chance is different. Another example, because it's a very important concept, looking at two categorical variables, see if they are independent or depend on each other. Like female left-handedness and right-handedness, is it depending on the gender? Is right-handedness independent of gender? Do higher does male or female had higher percentage of right-handedness? So what we can do is we're going to use the other method, which is the first one. Probability of A and B equal to P probability of A times B. If they're equal, they're independent. Okay, so we will just do probability of male first. How many males are there? So 43 plus 9 is 52, is 0.52. How many right-handed? How many right-handed would be here over the grand total is 0.87. So what is the probability of male and right-handed? Male and right-handed is this number, 43 over 100 is 0.43. All these are over 100. Okay, we're not looking at conditional, so it is like that. Now check if these two are equal. Probability of male and right-handed male times probability of right-handed, so it's 0.52 times 0.87 is 0.45. So look at this, they are very similar but a little different. So they're not exactly equal but very close. We conclude they are not independent. For them to be independent, they have to be exactly the same. But you can say, Ms. Chan, this is a sample. Maybe they are actually quite equal, but because of sample variation, they will change a little bit. So in chapter 11, we will visit this again to take into consideration of sampling variation. Yes, if this is not the whole population, it is a sample, so that sometimes it varies. You might have one or two that is different. So we would say this is actually quite close, so we can say that they are independent. But strictly speaking, in the probability point of view, they are not independent. So again, if they're the same, if you multiply this, it's the same as your n, then they are independent. Okay. And also lastly, mutually exclusive and independent are two different things. Mutually exclusive, just look at if they can happen together. So you look at whether there's a zero. And independent means checking either conditional probability or multiplying to see if it's equal to probability of P, A and B.